In the last video, we learned how to evaluate infinite limits algebraically. Here, we'll talk about finding vertical asymptotes and evaluating the limits around those vertical asymptotes, which will correspond to infinite limits. Vertical asymptotes occur at the zeros of the denominator that are not common to the numerator. To find vertical asymptotes when dealing with rational functions, recall that a rational function is a polynomial divided by another polynomial, we have a three-step process. 1. Factor the numerator and the denominator completely. 2. Cross out any common factors between the numerator and the denominator. When you are dealing with rational functions, common factors between the numerator and denominator result in holes in the graph. 3. Identify the remaining zeros of the denominator. These are the remaining undefined values of the function. These will be your vertical asymptotes. Let's look at some examples. Identify any vertical asymptotes, x equals a. Again, notice vertical asymptotes are written as equations of vertical lines, x equals a. Then determine the behavior of the function near those asymptotes by evaluating the left and right limits as x approaches a. So for each vertical asymptote, we're going to have to evaluate two limits, one approaching the vertical asymptote from the left, one approaching the vertical asymptote from the right. So let's find our vertical asymptotes. Again, we're dealing with a rational function. This is a polynomial divided by a polynomial. We begin by factoring the numerator and the denominator completely. Start off, always look for a greatest common factor. Notice that the numerator and denominator can both factor out an x, and from there we can continue to factor. This factors into x times x plus 1 times x minus 1 divided by x times x plus 2 times x minus 3. Next, cross out any common factors. Well, our common factor between our numerator and denominator is an x. We have an x and an x. We can cross those out. Okay, x equals 0 makes this function undefined. That's going to result in a hole in the graph. And the remaining zeros of the denominator are going to be the vertical asymptotes. So what makes the denominator equal 0 or the function undefined still? X equals negative 2 and x is equal to 3. So we have two vertical asymptotes in this function. Let's evaluate the limits to the left and right side of each vertical asymptote. Starting, we have the limit as x approaches negative 2 from the left of our function x cubed minus x divided by, and notice that I have left the denominator in factored form already because that was step number 2 of evaluating an infinite limit, right? We know that because there is a vertical asymptote at x equals negative 2, the answer has to be positive or negative infinity. And that's going to require us to use the factored form of the denominator. So let's try our direct substitution. We plug in negative 2 for x. Negative 2 cubed, that's negative 8, minus a minus 2, so negative 8 plus 2 gives me a negative 6 in the numerator. We plug in negative 2 into the denominator. This first factor turns into a negative 2 times, I get a 0 here. Well, again, when we have zeros, factors that give us a 0, we need to determine whether or not it's going to be a positive 0 or a negative 0. If I am approaching negative 2 from the left, that means I am slightly less than negative 2. And if I have a number that's slightly less than negative 2 and I add 2, I'm still going to be negative. All right, this is going to be a negative 0. So negative 2 times negative 0 times negative 5. We have negative 6 divided by negative 2 times negative 0 times negative 5. Notice in the denominator, a negative times a negative times a negative, that gives us a negative. We have negative 6 divided by negative 0. A negative divided by a negative, well, that's going to be a positive. And we get positive infinity, comma, d and e for our answer. The limit as x approaches negative 2 from the right now, the right side of this vertical asymptote. Well, again, the numerator is still going to give us negative 6 when we plug in negative 2. When we plug in negative 2 into our denominator, we look at the individual factors. The first one gives us negative 2. The second one gives us 0. But if I am plugging in a number that is just slightly to the right of -2, just greater than -2 by a tiny, tiny, tiny bit, and I add 2, I'm going to get a number that's infinitely close to 0 but positive. So that's going to be a positive 0. And a -2 minus a 3, well, that's a -5. We have -6 divided by -2 times positive 0 times -5. In the denominator, a negative times a positive times a negative. That gives us a positive. A -6 divided by positive 0, well, negative over a positive, that is a negative infinity for our final answer. Negative infinity, comma, dne. So there is the left and right behavior of our graph around our first vertical asymptote. Now let's look at our next vertical asymptote. The limit as x approaches 3 from the left. Well, we begin our direct substitution. We plug in 3 into the numerator. 3 to the third power. That's 3 times 3, which is 9, times 3 is 27, minus 3. That gives me 24 in the numerator, divided by, my first factor is going to give me a 3 when I plug in 3. 3 times 5 times 0. Now, again, with the ones that equal 0, we have to determine, is it a positive 0 or a negative 0? Well, if I have a number that is ever so slightly less than 3 to the left of 3, say, for example, 2.999999999, and I subtract 3, I'm going to get a negative 0, a number that is infinitely close to 0 but negative. So we have 24 divided by 3 times 5 times -0. That gives me a 24 divided by -0. A positive over a negative gives me negative infinity dne. And finally, the limit as x approaches 3 from the right. I try my direct substitution. Plugging in 3 into the numerator, I get 24 again. I plug in 3 into each of the factors. This gives me 3 times 5 times 0. But because I'm thinking of a number that is ever so slightly greater than 3, say, for example, 3.00000000001, and I subtract 3, I'm going to get a positive 0. This gives us 24 divided by 3 times 5 times positive 0. All of those are positive. A positive divided by a positive 0 gives us a positive infinity dne. And there we have our solutions, and we can verify this with our graph. Here is the graph of the function. Notice as I approach -2 from the left, the graph goes up and up and up, as we see from our first limit. As we approach -2 from the right, the graph goes down, 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 as we see in our second limit. As we approach 3 from the left, the graph goes down to negative infinity, as we saw in this limit here. And as we approach 3 from the right, the graph goes up to positive infinity, verifying the fourth limit that we found. All right, and again, what happens at x equals -2 and at x equals 3? Well, we have vertical asymptotes. And when x equals 0, here is our hole in the graph, right? We have a hole in the graph when x equals 0. That was from our common factor of x between the numerator and the denominator. Let's look at another one. Identify any vertical asymptotes, x equals a, then determine the behavior of the function near those asymptotes by evaluating the left and right limits as x approaches a. So we begin by factoring our numerator and our denominator. In this case, we have x minus 5 times x plus 1 divided by x times x plus 5 times x plus 1. After we factor, we cross out any common factors between the numerator and the denominator. In this case, the x plus 1. That means x equals -1 actually corresponds to a hole in the graph. Not worried about holes, so we cross out those common factors. Next, we identify the remaining zeros of the denominator. Well, what are the remaining zeros of the denominator? Those are our vertical asymptotes. X equals -5, and x is equal to 0. So we've got two vertical asymptotes again. We need to evaluate two limits for each one. So we evaluate the limit as x approaches -5 from the left of our function f of x. That's x squared minus 4x minus 5. And you could have left it in the factored form if you wanted to. You could actually even cancel out the common factors if you'd like, but I like to use the original form for my direct substitution and the factored denominator. So we plug in -5 for x. -5 squared, that's 25, plus 20 is 45, minus 5 gives us 40. Our numerator is going to be 40. When we plug in -5 into the denominator, we get -5 times 0, but because we are slightly less than -5, we're approaching -5 from the left. If I add 5, I'm still going to have a negative number. That's going to be a -0 times, plug in -5 for x, -5 plus 1 is -4. This is 40 divided by -5 times -0 times -4. Negative times a negative times a negative, that leaves me with a negative in the denominator. 40 divided by -0 gives me negative infinity dne. The limit as x approaches -5 from the right of x squared minus 4x minus 5 over x times x plus 5 times x plus 1. Well, the numerator is still going to give me 40 divided by, we have -5 times 0. In this case, however, it's going to be a positive 0 because I have a number that is ever so slightly greater than -5, say -4.99999999999. And if I add 5 to that, I get a positive 0. And I plug in a -5. -5 plus 1, that gives me a -4. So we have 40 divided by -5 times positive 0 times -4. A negative times a positive times a negative. That leaves us with a positive 0 in the denominator. 40 divided by positive 0, positive over a positive, gives us a positive infinity dne. And the limit as x approaches 0 from the left. So now we're looking at our second vertical asymptote. To the left of our second vertical asymptote, we do our direct sub. We plug in 0, 0, 0, minus 5 gives us a -5 in the numerator. If we are just to the left of 0, that means this first factor is going to be a -0. -0 times 5 times 1. -5 divided by -0 times 5 times 1. That leaves us with a -5 divided by a -0. A negative divided by a negative, well, that's a positive. Positive infinity dne. And now we can evaluate the limit as x approaches 0 from the right. So our x value is slightly greater than 0. Again, my numerator is still going to be -5. My denominator is going to be a positive 0 times a 5 times 1. -5 divided by positive 0 times 5 times 1. That leaves me with -5 divided by positive 0. Negative divided by positive gives us a negative. Negative infinity dne is our answer. And again, we could graph this function f of x to verify our solutions. Here is my first vertical asymptote at x equals -5. As I get closer and closer to -5 from the left, the graph goes down to negative infinity. As we get closer to -5 from the right, the graph goes up to positive infinity, verifying both of those solutions. As the graph approaches 0, as x approaches 0 from the left, we go up to positive infinity. As x approaches 0 from the right, we go down to negative infinity. All right. Again, vertical asymptotes at x equals -5 and x equals 0. And notice the hole in the graph as well when x is equal to -1. That hole in the graph coming from the common factors of x plus 1 and x plus 1. So here is your summary of what we have covered with limits so far. Whenever evaluating limits algebraically, always begin with direct substitution. If doing so yields a real number, that is your answer. If you do direct sub and you get a real number, you're done. If you get 0 over 0, this is the indeterminate form, the indeterminate quotient 0 divided by 0. You need to try additional techniques. Those where you're dividing out, your rationalization, and your simplifying of complex fractions. If you try direct substitution and you get a non-zero number divided by 0, then you are dealing with an infinite limit. Okay, the limit is either going to be positive or negative infinity. You need to factor the denominator and determine the sign of both the numerator and the denominator with your substitution.